So today we'll deal with yet another view of clusters. We've previously discussed a statistical view of clusters where we identify hotspots and cold spots and groupings of entities that meet a particular statistical test, like in the scan statistics. And now we take a little bit of a different view, more of a traditional statistical learning view, or some people call this machine learning now. It's basically data science. And in that literature, it's called unsupervised learning. Why is it called unsupervised learning? Because in contrast to, say, predictive analytics, which is a big word, where you have a training data set that you fit the model to and then assess the quality of the model on another data set and choose your model in function of that. In these techniques, there is no such control. So another distinction is in that predictive analytics, you have explanatory variables, or features as they're called in machine language, and a dependent variable. Here there's no dependent variable. So in the terminology of econometrics, in supervised learning there's a y and there's a bunch of x's. Here there's only a bunch of x's. And you want to use these to structure the data somehow to group them. So the readings, as I usually give you, this first reading is nothing spatial to it. It's about principal components and classical clustering techniques, which I'm assuming many, if not most of you, are not familiar with. If you are, then I could have done this lecture completely differently. But there's a very readable overview. You may be familiar with the classic statistical learning textbook by Hastie, Tibshirani, and Friedman. It's like this thick. It's really, if you want to do anything about machine learning and want to have a bit of a statistical background, it's a must read. Well, this one is kind of the baby version of that. It's much less technical, and it has extensive examples with R code on how you carry this out. And I particularly like the chapter that deals with principal components and cluster analysis. It's very readable. Then the other materials are much more technical, and they deal very specifically with spatially constrained clustering. One of the things we're going to see today is that traditional multivariate clustering doesn't deal with location. And oftentimes, or at least from my perspective, this is about spatial data. We're interested in clusters that make sense spatially, geographically. So in addition to being similar in a multivariate sense, which is the standard approach, they also have to be similar in a geographical sense. And remember, this goes back to the very beginning when we talked about what is a spatial autocorrelation statistic. Is the combination of attribute similarity with locational similarity. And so spatially constrained clustering does the same thing. It's attribute similarity combining with contiguity, with being compact spatial units. So there are a number of different algorithms. The first one in the paper by Asuncao et al. Is the one that we will actually illustrate in class and use in the lab. It just happens to be the only one I could find in R. There may be others, but I haven't found them yet. Then the Duc et al. Paper is a survey, fairly technical from an optimization point of view. Clustering can also be seen as an example of spatial optimization. In operations research, as an example of integer programming. This gets very technical, but the first half of it is more conceptual. GUO is an alternative to the Skater algorithm. As we'll see later on, they all have similar structures, but they have different ways, different takes on it. And then the last one I thought I'd throw in, because it's kind of it's not out yet, but it's available as a PDF on your Chalk site. It's kind of an interesting application of a lot of things that we talked about. You know, it uses principal components, which we'll talk about today. It uses spatial autocorrelation, local spatial autocorrelation, and then it uses spatially constrained clustering, and it's a big data application. It uses Twitter messages to kind of delineate linguistic regions in the US. based on the words that people used in Twitter messages. So it's kind of a cool application. What I'm going to talk about today is 3 specific topics. So first, I'll tackle the main problem. So the main problem, unlike what we've done so far, is too much data. So far, we've dealt with univariate situations, one variable, right? Autocorrelation, correlation of a variable with itself in other locations. Now we move into the multivariate world. And in the multivariate world, you often have many, many variables. And they're all somewhat correlated, sometimes not. So how do you make sense of this? And the first thing is that a lot of things do not work in high dimensions. So we have to reduce the dimensionality of the problem. I mean, imagine, you can imagine a line, a linear feature. You can imagine a space, 2-dimensional, 3-dimensional, cube, 4-dimensional. Most of us are out of luck already. Forget about 20-dimensional. You cannot visualize that. But you could take a 20-dimensional space, and data points are just points in this 20-dimensional space, and then project them on a subspace, such as a 2-dimensional space, and then we can see them. So that's one of the ways in which we can deal with dimension reduction. Then I'll spend some time on classic clustering methods, and there's basically 2 ways of approaching this. One is bottom-up, the other one is top-down. And to just give you a taste of that. And finally, I'll conclude with the spatially constrained flavor. And this could be a whole course in its own right, and I hope at one point it will be. But it's just scratching the surface, giving you a sense of what is the main issue, what are the problems, what are the approaches, and then illustrate one of them, which is not necessarily the best one, but is just one of them. So what are the principles? The main issue is what is known as the curse of dimensionality. And there's different ways to formally describe this, but in a nutshell, there's 2 big problems. Right? Low dimensional techniques developed for 1 or 2 dimensions, break down in high dimensions. They just don't work. Right? And the other thing is that sometimes they do work, but they get to be so complicated and, in a sense, so inefficient that they're not usable. So to give you 2 illustrations of this, and I really like these because they kind of get the point across, and they come out of this statistical learning book. I didn't make this up, but think of the following problem. So first of all, 1 dimension, right? Just a line. Let's think of a unit line from 0 to 1. And you have observations that are uniformly distributed over that line. So there's randomness. They're not deterministic, but they're uniformly distributed over the line, right? How far do you have to go if you start at 0? How far out do you have to go on the line, on average, to get 10% of the data points, right? Or 20%, or 50%. In a linear space, that's exactly that percent, because the way it's uniformly distributed. So on average, if you want 10% of the data points, you go out 0.10 of the unit distance, right? In 2 dimensions, right? So now we have a square, a unit square, and the points are uniformly distributed on the unit square. We'll do that, Julie will do that next week, as that's spatial randomness, complete spatial randomness for a point pattern, right? So now we don't have a line, but we have a little square. And how big does that square have to be? So what is the side of the square to capture 10% of the data? It's no longer 0.10. It's bigger. It's more. And that's what you see on this curve. So on this side, oh, you can't see it. So here, let's say this is 0.10. So you go up. It's a little bit maybe misleading because the scales are different on the horizontal and the vertical axis. So this should really be a 45% line if it's the same scale. But so you go up and you have 10, right? If you want 2 dimensions, you go up and now you're at 30%. So the side of your little square no longer has to be 0.1 but 0.3. Okay, now we go to 3 dimensions. And remember when we did the three-dimensional scatter plot in GeoDa, how hard it was to get the little cube to work to catch points in the 3D. If we go to 3 dimensions, to get 10% of the data, we have to get over 0.45. So this cube that we have has 0.45 as its side. So in other words, the higher the dimension, the more inefficient, the harder it is to get 10% of the data points. And why is that? Because with each dimension, there's an additional complexity added to the point. So the points can float further away, so to speak, by adding these additional dimensions. So even though they're uniformly distributed in that dimension, they're actually further from each other. So you have to have bigger and bigger boxes, so to speak, as you go to higher and higher dimensions. And, you know, if you go to 10 dimensions, I mean, the example I will use for the clustering has 12 variables. So 10 variables is even less than that. You have to get almost 0.8 of the 10-dimensional, if you can even think of it, 10-dimensional space to capture just 10% of the data. So this is one example where a low-dimensional technique basically breaks down in high dimensions. It just doesn't work. Another example, which is, I think, very useful because we use this notion of nearest neighbor distance a lot in point pattern analysis, and we've used them in the weights for k nearest neighbors, for example, is the same thing. You know, if you have random pattern of points on a single dimension, how far do you have to go on average to reach the nearest neighbor? And that's, say, this band. If you go to 2 dimensions, it's more than double. And so this is another example. If you up the dimensionality of the data, the size of the ball, so to speak, that you need to capture the nearest neighbor. So in other words, there is no data point in this ball. It's empty. It grows exponentially with the dimensions. So k nearest neighbor sounds really good as a technique to group things together, but in high dimensions, it becomes very quickly highly inefficient, right? And so then you have to think of other ways to deal with this. And so what are some of the ways that we deal with this? 2 that I will illustrate. There's others, but they illustrate 2 kind of basic principles by which we can tackle this. And the first principle is, well, you know, why use all the variables, right? So we have, you know, in the example, 12 variables. Why use all 12? They're intercorrelated, so maybe we can replace them by a lower dimensional set of variables that are functions of the original variables. So we replace in some reasonable fashion, and we'll see in a few minutes how we do that, these many, many variables by a small set of other ones that are, of course, related to the original variables. Otherwise, it wouldn't make any sense. And principal component analysis is one example of doing that. Another way of thinking about this is very spatial. All this stuff, even though it's non-spatial, you know, by construction, is actually very spatial in the way that it thinks about multivariate data. You can think of multivariate data as point floating in higher dimensional spaces. And how do you figure out which points are closest to each other and which points are further apart? So it's very spatial, even though it's not geographical. You know, it's so one way to think about this is to get down to a dimension that you can actually visualize. So you project down. You lower the dimensionality in some, again, organized fashion. And the way, the technique that I will be illustrating is multidimensional scaling, where you focus on the distance between the points. So you can compute a distance in higher dimensional space. It's just an extension of Euclidean distance. You know, Euclidean distance, you know the triangle, you sum the 2 perpendicular parts, they're squares, right? If you go to p dimensions, you can have p of these squares differences, and then it's the same concept, but extended to higher dimensions. So you have your points floating in high dimension, and you compute their distances, the distances between them, can you find a lower dimensional representation that not reflects, but respects that distance ordering as best as possible, right? I mean, this is a nonlinear optimization problem. So find point locations in a low dimensional space that respect the distance relationship in a higher dimensional space. And that's an example, that's what multidimensional scaling is about. You also have different ways of projection pursuit, which is a way of basically flipping higher dimensional spaces, projecting them onto lower dimensional spaces, and then looking for structure in that way. So basically, the bottom line is we don't like these high dimensional spaces. We have to deal with something that we can handle, that we can see, that we can visualize. So the first technique is principal components. So what's the idea? We have P variables. So typically these are high dimensional, and this is actually really relevant, I mean, should I say in political marketing, and that's why it's unsupervised. It doesn't always work. So you try to categorize a population into subgroups that are similar with respect to a number of characteristics. Also in marketing, you have typically many characteristics on clients, but you only have, very few stores. So in a tradition, this is the opposite of what you always see in regression. In regression, you have fewer variables than observations. These are often situations that are the reverse, where you have many more variables than observations. It's the opposite of your textbook statistics example, right? So what do you do with that, right? So you have 70 observations on 70 stores, but you have 200 characteristics. You can't do a regression. It falls apart. So you have to reduce the number of characteristics to something that is meaningful and that you can use in a regression with 70 stores. And so the idea here is that these P variables are intercorrelated, and that can be reflected by a variance-covariance matrix, or if the variables are standardized already, so mean 0, variance 1, then you have simply the cross-product matrix. And that's a square matrix, P by P square matrix. And if you guys love eigenvalues the way I do, then you know that you can simplify the structure of that matrix in a number of different ways, right? So that's what these principal components are. So typically, you have many fewer than the original number of variables, and you want to pick those that capture most of the variance, most of the variability incorporated in this covariance matrix. And you want to do this in a way that is efficient, so you want those principal components to be orthogonal to each other. In other words, they're not correlated. And you may remember from your stats class or from your econometrics class, although economists really don't like this too much, sociologists do, is that when you have multicollinearity, high degree of multicollinearity, you can replace your variables by a small number of principal components. By construction, these are uncorrelated, so you will not have any problem of multicollinearity at all, right? And then the final thing that you do is that you scale their coefficients, otherwise you have an identification problem. That's just a mechanical thing. Okay, so what actually happens here? So we call our component C. Every observation gets a score on this component, and it is nothing but a weighted sum, a weighted average of the original variables. And I'll give you an example in a second. So you have a bunch of different, in the example I'm using health characteristics for community areas in Chicago. So we have 12 of these. That's too much. We'll reduce them to, in my example, 4. And each of these 4 is a weighted average of the original 12, right? And they're orthogonal, so their cross product is 0. They're uncorrelated. You can think of it that way. And then also, for practical purposes, these coefficients, they're called loadings in the PCA literature, the A's. are scaled such that the sum of their squares equals 1. That's just a convention to make things comparable. And the reason why you need to do this is because we're dealing with the contribution to the variance. So if you don't somehow rescale this, then a single variable with a lot of variance would dominate the whole thing, and you don't want that. Now, there's some modern versions of this principal components that actually purposely, similar to this idea of a lasso that you maybe have heard of, they purposely limit the number of non-zero loadings. So in the classic approach, each variable will have an A coefficient. In some of the more modern machine learning implementations, you have a trade-off function so that you force some of these A's to be 0. In other words, your components are easier to identify. Of course, in the extreme, you're back to where you started with, right? And each component is the original variable. So it's this tension between giving a weight to all of them versus giving a weight to only one of them, and then we're back to square one. We have to be somewhere in between, and that's an optimization problem like everything else. How do you compute this? I won't give you the technical details, but it's basically a matrix decomposition. Easiest way to think about this is eigenvalues, although in most modern practices they're not actually used. There are other ways of decomposing a matrix that are much more scalable. So what do we get out of this? We get, for each principal component, these A coefficients, which we call the loadings. So that allows us to say, for example, does variable 1 contribute in a positive way or a negative way? You have the signs of the loadings, and you have their relative magnitude. So you can, in some social sciences, in sociology, there's a whole tradition of interpreting these loadings and then giving these new components a fancy name, right? This is social stress, or this is some culture, this is something else, right? Factor analysis is a version of this. It's not the same thing, but it's very similar in mathematically, at least, right? So that's often very hard to do, right? That's why these regularization techniques come into play, which make it a little easier to maybe interpret the variables. If you set a bunch of these coefficients to 0, maybe, one set of components is cancer, another set of components has to do with heart disease, and then, you can give these things names that make sense. Then obviously the other so that's the loadings. The other thing you want to know is how does each observation score? So you create the score for the principal components. So every observation has a new value. You can think of these as new variables, and then you can look at how similar the observations are with respect to these variables. And then also you want to know how good they do, how well they do in terms of explaining this overall variance, right? Do you need, how many components do you need to explain 80% of the variance, or 90% of the variance, or if you're not too picky, 50% of the variance, right? And you can think of these components, again, as an approximation of a higher dimensional space. For example, if you have 3 original variables, then a 2 principal component space is the plane that fits those points in 3D the best, the closest. So again, it's a lower dimensional approximation to higher dimensional representation of the data points, right? So you can think of, if you have 12 variables, that's a 12-dimensional space. Your data points are floating in 12-dimensional space. Your first 2 principal components give you a plane that approximates these 12-dimensional space points in the best possible way as a plane, as a 2-dimensional space. So I mentioned I take these 77 community areas. I did that because it's 77. That's a small number. That's easy to do. And I have a whole bunch of health indicators. Actually, Marinia put this together for a project that she's doing. So you have all kinds of bad stuff, right? infant mortality, different kinds of cancers, stroke, heart disease, all kinds of stuff. So this is what it looks like if you do a principal component analysis. So you see here all the variables, principal component 1 with its individual loadings. So for this one, they turn to be all positive, right? All the loadings are positive. For the second component, some are negative, like I'll point it out again later, but if you look at some of the cancers are all negative, whereas in the first component are positive, and so on. So then the art, where the social scientist comes in, is to make sense of this and to say, well, these loadings are such that this represents this particular dimension of the data. I won't go there because I don't know enough about this stuff, but you can see that they're not all the same. Some are much larger than others, and some are positive and some are negative. So they kind of combine the variability, original variability in these 12 variables into a smaller dimension. And we can represent this, and we can, these are the first two components, and each point is a data point. So you take your score on component 1 and score on component 2 and put them in two-dimensional space. So one way to think about this is that if you find points that are close together, these observations are very similar on these two dimensions of the data, right? So that's similarity in attribute space. A particular kind of plot that is useful in this particular context is called a biplot. And what a biplot does, it shows as a vector, as this arrow, the contribution of the loadings to for each variable, the loadings, how the loadings contribute to the principal component. So you have two things here. One is the two-dimensional plot. These are the scores. These are the results of the components for component 1 and component 2. And then the red lines give you how these components are made up. For example, the tuberculosis one, which almost shoots straight up, tells you that it has a very low loading on principal component 1 and a very high loading on principal component 2. So if we go back here, we, where is it? It's the bottom one. So you see 0.01, it's almost nothing on component 1, and then 0.6 on component 2. So this is how you look at this plot. And the interesting things to notice are arrows like that. What you don't like and don't want is an arrow that's at 45 degrees. Basically, that's saying both this variable contributes equally to both components. So that's really hard to interpret. What you like is either these very steep ones or these ones that are negative, because they tell you positive in one dimension, PC1 dimension, negative in the PC2 dimension. So that's an opposite loading for the two dimensions. So those are our principal components. They allow us to summarize the variability over the 12 dimensions. And then just to illustrate, how this works kind of behind the scenes, this is all related to the eigenvalues, but these eigenvalues can be related to the proportion of the variance that's explained. And so the first component explains the most, 55%. The second component explains almost 14%. It's almost a third of the first one. So it drops off very quickly, and together they're basically at 70%. So the first 4 components explain 80% of the variability in those 12 variables. So for most practical purposes, you could say that's good enough. And so I'm going to work with those 4 instead of working with the 12. And this is plotted in something that's called a scree plot. And the scree plot comes up in a couple of other techniques as well. Basically, what you're looking for is an elbow. This is called an elbow, like this. So it goes down very quickly, and then it flattens out. Now, you may say this is very wishy-washy, and it is. There are tests. There are formal ways to summarize this, either looking at the eigenvalues or some drop-off in the variance explained and things like that. So I'm not going to go there, but basically you see what I mentioned before. By the time we get to number 4, then it basically doesn't give us too much more power by adding additional components. So this is called a scree plot. You use a scree plot to figure out how many components you will use in the analysis. Okay. And then you can map the principal components. You can even do local Moran analysis on the principal components. And if you know Chicago a little bit, you know Chicago is very segregated and very stratified, should I say. This scores very high on this first component. This is the south side. This scores very low on this first component. And so this gives you an idea of how this multivariate interaction is represented in space. It's contiguous, yeah. Well, you can, but it's a different notion. You have to define your notion of covariance. Okay, and there are ways to define that. So you have to define how similar is, category 3 versus category 4, because they're not ordered, right? So, and I forgot the name, but there is, in the machine learning literature or statistical learning literature, there are measures of similarity for categorical data. But it's trickier, and it's not necessarily exactly the same, but it's similar in spirit. The other thing to keep in mind, though, is that, and I'll keep hammering on this because then at the end we'll put everything together, is that similarity in multivariate space. So these are our 2 dimensions again, and these 2 points are basically almost on top of each other, which means that their scores on the first 2 principal components are just about identical. And this is purely by chance. I was extremely lucky. I was just looking at this, and then it turns out this is Hyde Park and the near north side. So Hyde Park and the near north side have basically the same profile when it comes to these first 2 principal components, which are summaries of 12 health indicators. But of course, they're not contiguous. So they could be part of a cluster in multivariate attribute sense, but they're definitely not geographically connected, right? And this is an issue we're going to keep running into. Remember, when we talk about spatial autocorrelation, it's both. It's the attribute similarity and locational similarity. Here we have the attribute similarity. We don't have the locational similarity. Okay. That's principal components. I'm going to have to speed up, unfortunately. So the second one is multidimensional scaling. Yeah. To measure breaks in space? Well, I guess you could. I think the breaks in space are better addressed when you move to actual clusters. And then you see how observations group themselves, and then how that is or is not reflected in space.
So having more clusters and then less of them together. And then
yes. Okay. Yeah. And then at the end, we will force them to be together. And then, of course, there will be a trade-off between the clustering purely on the attributes and the clustering that takes the space into account. We'll talk about that in a few minutes. Okay. So multidimensional scaling is this projection idea, and it's actually really cool, and it's related to a lot of the math that is behind projections and conversions between projections, this topic that you all love, map projections. So you go from a sphere to flat. How do you preserve the distances on the sphere on a flat projection? And this is the same kind of mathematical apparatus. So we have our n observations in a hypercube. We have the distance, Euclidean distance in p dimensions. As I mentioned to you, it's a very straightforward generalization of the triangle, theorem. So you sum the square differences over p dimensions, and then take a root or not. That depends. And so basically, we want to go lower dimensional, right? We at most p minus 1, but typically much smaller. So in my example, I'm going to go from 12 dimensions to 2. And so 2, again, we can represent very clearly. So the formal way to deal with this is that we have our p-dimensional distance, and then we have a stress function. An objective function that tries to minimize the difference between this original distance that we have and the distance in lower dimensional space. So we try to solve for the coordinates in low dimensional space such that this is minimized. And there's a number of very classic, very well-known ways to do this. It's basically an optimization problem, right? And then you get the coordinates, and so you put the points in a map. Or in a plot, sorry. You can put them in a map too, but it's not the same. So it's not the same as principal components because you can't map these. These are coordinates. So principal components are values for the observations, so you can map those values geographically. This you can't map geographically, but what you can do, of course, with linking and with brushing is find out where are these points that are very close together. And so, of course, you see me coming a mile away. That's what we're going to be doing. And so I picked up, again, randomly on these 3 points, which are very close together. So this means that if you project their location in 12-dimensional space down to a flat plane, they are very close to each other. Now, that may not be good, right? The idea is that presumably, as our algorithm works, that their distances between them in 2 dimensions reflect the distances between them in 12 dimensions. So in 12 dimensions, they should also be close, right? But you see that some of these may be adjoining neighborhoods, but then some are not. So again, we have this tension between attribute similarity and geographical similarity. Okay, so that's the dimension reduction part. So typically, the way you do this in practice, you first go through an exercise of dimension reduction where typically you come up with a smaller number of principal components, and then you move into the clustering analysis, because you don't want to do clustering analysis, say, on 80 variables. That's just, you can, but why would you if, 3 or 4 of these principal components capture most of the variability in your 80 variables anyway, right? Of course, you lose a little bit, but you gain a lot of transparency and insight in the process. So the principle behind classical clustering, nothing spatial involved here, is very simple. So you have a bunch of observations, and you want to group them such that the members of the group are as similar as possible, and that the groups are as different as possible, right? So you put the likes together. This may not be appropriate for everything you do, but that's the principle. So there's basically, again, an optimization process. I have n observations. How do I put the n observations in k groups so that each group internally has the smallest variance, so to speak, is as similar as possible. And then, usually automatically between the groups, they are as dissimilar as possible. So if you look at income, you have high income and low income, right? And it's very clear, very separate. And each observation, as opposed to fuzzy clustering, in hard clustering is only member of one group. If it's fuzzy, then there's a membership, the degree to which you belong to a group, which is a little bit different. But so this sounds like a simple problem, And in some respect it is, but in other respect it really isn't. First of all, how do you define similarity? We can take our Euclidean distance again, or we can take correlation, or we can take a cosine similarity, which is yet another way of measuring multivariate similarity, right? Second one, million-dollar question, how many groups? What is K? Is K 4? Is K 6? Is K 25? You know, again, there are many rules of thumb, and there are obviously objective criteria to assess what is a good K, because you have the measure of internal similarity, and you have the measure of in between dissimilarity, so you can see how these stack up with respect to that. And of course, keep in mind, this is a mathematical problem, but it has two very simple solutions. One solution is that all observations are one cluster, and the other solution is that each observation is its own cluster, right? And so we want something in between, because neither of these are useful for our purposes. So how many? That's a really big question. And this is not a simple problem. It is, as it's called, an NP-hard problem, which is basically something that you cannot practically solve by enumerating the solutions. So it's an easy problem, right? You have n observations that you have to put in k groups. How many of these can you do? Well, it's k to the n, right? And in our very simple problem, I was trying to figure out how I would express this to you. So we have 4 clusters. We will have 4 clusters. And we have 77 neighborhoods. So we have k to the n, which is 2.3 times 10 to the 46th. And what was I coming up with? You know, 10 to the 46 is a little less than 10 million times 10 million. That's a lot. That's 46 zeros. That's a lot of zeros. So, you know, if you have a super fast computer, you could enumerate them all and figure out which one is the best on your objective function. And this is basically a toy problem. So you could still actually do this, right? But if you have, you know, a city of 6 million people, and you try to put them into whatever it's called, Prism or something, these different marketing characteristics, and maybe there's 30 or 40 of them. Okay, 40 to the power 6 million, forget it, right? It's not going to work. Yeah. So the challenge is to come up with algorithms, with heuristics that get you something as close to the global optimum as possible. I mean, as this is a highly nonlinear problem, there is no guarantee that you actually have the global optimum, because you can get stuck in a local position that you think, oh, I'm doing great, but in fact, you're not. So how do you get unstuck? That's a big challenge in this process. So just to simplify a huge literature, I tend to do this, you know, two ways of going at it, from the top or from the bottom, right? So hierarchical clustering, as it's called, starts from the bottom. And so I'll illustrate in a second. Basically, you start grouping. You start with all n observations as their own cluster, literally. And then you start putting the two together that are the most similar. And then you keep doing this until at the end, there's one cluster with all of them. So you move from the bottom to the top. And this will be visualized in a graphical tree structure. So that's where the bottom to top idea comes from. And the other approach is, you can think of it as top-down. It's not quite the same. It's called partitioning clustering. The best known measure is k-means, but is by no means the best one or the most appropriate one. Is just I think the better known one, is where you start by randomly assigning each of your n observations to one of k groups. You pick k, right? And then you start reshuffling to get better and better measures on your objective function. So you reshuffle them so that their internal variance goes down and the in-between variance goes up. So that's an optimization problem. There's, in all but a few simple cases, there is no analytical unique solution. You use heuristics to work this out. So this is not an understatement. There are many, many clustering algorithms. If you look at any book on data mining, you will see them. You know, they all have different fancy names and typically have specialized software to solve them. Some scale well, some do not scale well. It's a huge literature. So just to set the stage, hierarchical clustering, the algorithm, as I said, is very simple. You pick the two that are closest, and then you take the next two that are closest. Now, the tricky part is that you have to define what you mean by closest. And that's simple when you have two singletons, so to speak, so two observations. It's square difference or whatever you take, right? But then once you start grouping them, how do you measure the similarity between a group and a singleton, or between two groups? And that's where it gets complicated, because you can do that in many different ways, as I'll show you in a few minutes. And then you just keep going, and the end result is a tree structure, or dendrogram, as it's called, which basically shows you how you combined these units from each being their own cluster to all being in the same cluster. It's a cool drawing. So this I picked out of this book that is not quite out yet. I just checked yesterday, and it's still, you know, pre-release. But it's on GitHub, so you can actually look at the book. It's by our studio guys, Grolemund and Wickham. And I find this one of the most intuitive explanations of hierarchical clustering. So just imagine these 8 points in two variable space. And so we start by picking the two that are closest, right? So 2 and 3 are the closest. And then in the dendrogram, that connects them, right? And the height of the horizontal bar doesn't necessarily mean anything. Sometimes it does, but it just means this is step 1, right? And so then you look at what's left, and 5 and 7 are the next two closest ones. So you put them together, and then in the dendrogram, you see the little connection between 5 and 7. And it's a little higher than the first one. Now, first thing to keep in mind, the labeling is irrelevant, right? So you could put 3 in front of 2. Same thing, right? So we continue. Now it gets a little more complicated, because now we have to figure out whether these groups, 2 and 3 together, are actually closer to 1 or closer to 5 and 7 together, and so on. So let's just say we keep on going, and we keep on going until we're here, and now we're done. So every one of the 8 is in the tree. At the top of the tree, 1 cluster. At the bottom of the tree, if you wish, 8 clusters, right? So then we cut the tree. We cut the tree at the level, at the number of clusters that we want. If we want 2 clusters, we cut here. So we have 2 of these branches, and they're defined by the branches and the leaves under them. So you cut the tree, and you see what falls out. If we cut a little lower, you get something that is very typical of clustering, is that you end up with singletons, with observations that are their own cluster. What does that mean? It basically means that they're so different from the rest that they don't belong with anybody. They're not playing well, right? And this happens. Now, a very important practical issue is, how do you formally measure the similarity, not so much between two observations. I mean, that's an issue too. Do you use correlation? Do you use distance or whatever? But between groups that consist of multiple elements. And this is called the linkage between the groups, between the clusters. So you have complete linkage, single linkage, average, centroid, etc., etc. So this matters, as I'll show you in a few minutes. The complete linkage tends to give you more compact clusters. The single linkage tends to give you elongated and situations like I will illustrate where you have one big cluster and then a couple of singletons, which is not that useful necessarily. But it's good for some reason. So, and that's just ignoring the million-dollar question, where do you cut the tree, right? But you, again, this is an iterative process, right? So you cut the tree, you see how well it does in terms of the objective function, but also you see whether this makes sense, right? Are you putting observations, in a marketing sense, clients together that actually belong together, or are you putting things together that don't really fit that well together, okay? So again, from the same book, a really cool illustration of these 4 of these possible linkage methods. So complete linkage takes the distance between the most extreme elements from each cluster. So you basically, the similarity between the 2 clusters is the distance measure between the points that are the furthest apart. Points being, of course, data points. Single linkage is the other way around. You take the distance between the points that are the closest together. Average takes all of them, all the, two-way distances, and takes an average from them. Centroid puts the point in the middle. You all know what a centroid is by now, so you can do centroids in multivariate space as well. And each of these will give you slightly different results. This is the example using the first 4 principal components in my health data. This is the dendrogram that you get from complete linkage. So it's all very nice. You see they put them two together, and then you can cut this. How many clusters do you want? You want 4, you want 6, you can cut this, right? And this is an example of the maps that result. And you see that by and large, these, especially the 6th one, these groupings tend to have some geographical content to them because these variables are all highly spatially correlated, but it's not perfect, right? So you have this cluster here with then 1 element there and 1 element over there and a couple in the north. So again, we have this tension between the attribute similarity and geographical similarity. This is what you get with single linkage. And of course, we're not going to like this because this is the cluster that we get. So 1 cluster is everything except 3 singletons. Right? If we go to 6, it doesn't get any better because now we have 5 singletons. Right? So that's a result, and only result, of the criterion that we use to define the similarity between the clusters. So single linkage takes the closest points in each cluster. Complete linkage takes the most extreme points in each cluster. So if you do this a lot, you get to have a sense for this. K-means clustering is, as I said, the other way around. Is a partitioning method. You assign, you start with an initial solution. You compute some measure of central representative point, a centroid or something else. Then you reassign the points and keep doing this over until it converges. And this is the problem of potentially ending up with a local optimum because the first starting point is random. And as we'll see in the lab, this is where you set the seed because otherwise you cannot replicate your clusters. So typically the way you do this in practice is you generate 20, 30, 50 initial solutions randomly. Then you pick the one that does the best on your objective function and take that as your starting point. And then also to make sure that you're not getting stuck in a local optimum, you change the seeds and then do another set of random starting points and see if you end up with the same thing. So if you end up, and the same thing I have to point out, and I mentioned this already, the labeling doesn't matter. It's the grouping that matters. So in a k-means, the first time around, you could have cluster 1 that consists of A, B, C, and D. And in the second exercise, A, B, C, and D is cluster 5, but it's the same grouping. That's what matters. So labels are irrelevant. Again, out of the same book, although I think they made a mistake, but in terms of the grouping. So you take the centroids, then you assign them to the centroids. See, I think those top green ones should really be assigned to the blue X, but I didn't figure it out. But you get the idea, right? So you keep reshuffling, reshuffling, reshuffling until there's no more change. Basically, you look at your objective function. If your objective function doesn't improve enough, you stop, right? And you say this is it. Bottom line, what is K, right? And here you can look at the objective function, and the take-home point is that there is not necessarily a unique solution, right? It depends on your purpose. So sometimes you want a grouping that maybe doesn't have the best measure on your objective function, but it's good enough and it makes more sense in terms of the grouping of the initial observations. Be aware of the sensitivity to the initial random assignment. Have to do sensitivity analysis to see if, I mean, you never know this for sure, but if you try enough different starting points and you always end up at the same thing, you can be fairly confident that you do not have a local optimum, but that you're not trapped, in other words. And then for replicability, you set the random seeds. So this is, you just crank the machine and you get the, for example, K equal 4. You end up with 4 clusters, sizes roughly equal. That's something that you like. That's, and there's the criterion of the within cluster sum of squares, and then also the tension between the total sum of squares and the between group sum of squares. Now we go to 6, and then with 6, of course, one of them is a singleton, so it's within sum of squares is 0. And then we do a little better in terms of the overall share, but having singletons is not a good clustering outcome, So you really ideally don't want this. And then, of course, you can map them and see where they are. And they are somewhat similar to what we found with the hierarchical clustering, but there are some differences. If you have time, you can look at the map. And in the lab, you'll be doing this stuff. So just as a technicality, the way I make these maps, it's always the same thing. So I do the clustering actually in R. Then I have the cluster labels. I bind them to a polygon ID, write a CSV file, merge it in GeoDa, and make a unique values map. And so it's really, you can do this in R as well. In fact, in the lab, you will be doing one. You will be making a map in R. Okay, so this is the non-spatial stuff, hierarchical versus partitioning, right? Spatial stuff is called regionalization. There's a number of different terms for this. One very, very critical application of this is redistricting. Redistricting creates regions of ideally identical population size, because one person, one vote. So you don't want one district where, the congressperson represents 500,000 votes, and in another district it represents 10 million votes. I mean, it's not perfect. You can't totally do this because they have to be grouped within states, and so it doesn't add up very often. And some small states get away with stuff. But anyway, this is a very important application of this type of technique. There's other applications that are more of a statistical nature. I mentioned the rates problem, the small area number problem. So you have, you do an analysis, say, at the census tract level, and you're looking at mortality for a particular disease, and you don't have enough people, right? So how do you come up with an area that is not an administrative district per se, but is a grouping of smaller areas, and that has your minimal critical population? Let's say you want to have at least 50,000 people in your area. So how are you going to group these initial atomic areas into larger groups that are contiguous? They have to be connected and reach your target population or reach some other kind of objective function. So this is, in essence, a multi-objective optimization problem. So you have single objective optimization problems, which is like minimizing least squares. That's a single objective. When you have multiple objectives, then you have to deal with the trade-offs between the objectives. So here you have at least two and often more objectives. So the first one is just what we've always done, the classical clustering objective, within cluster similarity, between cluster dissimilarity. The second one is we have to get spatial similarity defined. Typically, that is by contiguity. And then there's a whole slew of other potential objectives that have to do with the shape of these regions that we end up with. You know, so the term gerrymandering, you're probably familiar with that term. The original use of that showed a snake-like shape by which wards were strung together to form a district. So that doesn't meet the compactness criteria. And in redistricting, there's a lot of debate about how compact should these districts really be, and so on. But basically, my point is, we're not done with these two, right? There's a whole bunch of other ones that you can bring into play, having to do with the shaping of the resulting regions. You can bring in minimum population size, maximum population size, and other types of constraints that pertain to that. So how do we do this? Right? There's a number of different ways to approach this. I'll focus for this class on a graph-based approach because I find it very intuitive. But basically, you can start with what we already have. You can take one of our solutions that we had and start shuffling around. So you say, for example, if you remember, I'm not going to go back, but if you look at a map, so you have cluster number 4 has a bunch of community areas here and then one over here. You say, well, this one I'm going to kick it out. I'm going to move it either by itself or into another cluster. So you start with the classical clustering solution and then update it. I'll talk a little bit more about that in a second. Second one is a multi-objective approach where one objective has to do with attribute similarity, the other one has to do with locational similarity. Same old story. Automatic, you know, a heuristic that just kind of groups them and maximizes an objective function. Graphs represent a similarity, both in terms of attributes or in terms of space, by a graph structure. We've done this when we looked at spatial weights. If you remember the spatial weight structure in R, we drew a little graph that connected each spatial location to its neighbors. That's used. And then, as I mentioned, in operations research as an integer programming or mixed integer programming optimization problem. So the classical approach starts with hierarchical or k-means and then combine or split clusters that are not contiguous. It's very inefficient, and also you have no idea how many clusters you're going to end up with. So in your classic approach, you might say k equal 4, but then after you're done reshuffling, you may end up with 7 or 8, right? You don't know. It works, but it's not very efficient. It's not very good. Then the multi-objective approach sounds really intuitive. So basically what you do is you include location as one of the variables. And for example, we could do k-means on PC1 through PC4 plus x and y. So instead of 4 variables, now we have 6 variables. And if we're lucky, that will force them to be more together than originally. Yes, but not completely, because we have to figure out the trade-off between the similarity in space and the similarity in attribute space, so to speak. So really, you can think of this as an objective function with two parts. One part is to make sure that they're all contiguous. So, you know, you could do this just by itself and just group the areas that are closest together, period, without looking at the attributes at all, right? And then you could do the same on the other side, grouping them together, only looking at the attributes, forget about the location. And those are two different solutions, right? So how do we weigh one part of the objective versus the other part? That's the tricky part. And typically, this is a trial and error process where you go through the exercise with different kinds of weights. This is pretty much abandoned as an operational technique because there's much better ones. This is a classic article by Openshaw and Rao. It's called Automatic Zoning Procedure. It was a little crazy at the time, but it's fairly old, but it's an optimization process. It's a heuristic that just starts with random grouping and then just kind of puts them together in better and better ways. Contiguity enforced, but also similarity plays a part. That's very similar in spirit to the optimization routines. The graph-based approach, so you introduce the contiguity structure as a graph, as we've done when we talked about the weights, and then you prune the graph, meaning you cut it. And one technique, this skater one it's called, they called it skater. You just cut the graph so that the groupings that you end up with are internally the most similar, right? And we'll see in a few minutes how you actually do that. It's pretty clever. As it turns out, that's actually a constrained search of all the possible solutions. So by forcing yourself into this graph structure, you're eliminating some potential solutions. Now, as long as you're not eliminating very good solutions, that's okay. But you don't know that, of course, when you start the process. So there's some criticism of this approach, but it's very intuitive, and I'll use it as the example. And then this is the cat's meow. This is how, if you really want to do this right, this is how you do it. You set it up as an integer programming. Integer programming is where the decision variable is 1 or 0. So basically, you can think of x, I, j. X is observation I belongs to group j, and it either does or it doesn't. And then you have an objective function, which is always the same one, with some contiguity constrained as part of the constraints in your optimization problem. I mean, if you've never done this, you have no idea what I'm talking about. But if you have, then it all makes sense. You have an objective function, then you have a bunch of equality and inequality constraints, and you just find the zeros and the ones that maximize your objective function. Now, one of the problems with this is that it doesn't scale very well necessarily. And so there's all kinds of very clever heuristics to allow this to scale better to larger solutions. And that's really a very fun, to me, mathematical set of problems. So just to illustrate this, the Skater cluster analysis, it stands for spatial cluster with cluster misspelled, and I have no idea why, analysis by tree edge removal. That's the name, the title of the article. So it uses a concept which I thought the reason that besides the fact that it's in R, the reason that I like to talk about it is it introduces a couple of graph theory concepts, and these are good concepts to be exposed to if you don't know them already. And it's the concept of a minimum spanning tree, which is one way to simplify the graph structure of a network. I mean, you can think of contiguity as a network representation. So we can simplify this in the minimum spanning tree, and then we're going to cut it. So it's actually very simple. So here, these are the 77 community areas. So the lines are contiguity. We've done this before. This is based on a weights matrix. Actually, the way it's done in R uses a weights matrix, our neighbor list. That's the basis for this. Now then, what happens is, so this is just the weight structure. Now we're going to give each of these connections a value. So it becomes a weighted graph. Okay? And what's the value going to be is the dissimilarity between these two nodes. Okay? So because we now have a value for each link, we can cut this graph, and then we can measure the subparts. We can measure them on our objective function, which is basically based on these weights. So in its original form, these weights are just distances, and you want to find a tree that connects each location by only going through it once, right? So the tree will have n minus 1 nodes. I mean n nodes, n minus 1 edges, sorry. So the nodes are the points, the edges are the lines. So one less, so everybody is connected with one other one, and you pass through all the one. So you can do this in its initial geometric form. This is a geometric, computational geometry problem. So you have this as the distances. So how do you travel through all the points with the shortest total distance, right? So the translation of this using attribute similarity is that now the distance is not geographical distance, but is the dissimilarity between those two. For example, the dissimilarity as a Euclidean distance on the 4 principal components, right? Other than that, it's completely the same. We have weights for each of these things. How do we connect all these so that we pass through them just once and minimize the overall weight, the overall dissimilarity? And this is your minimum spanning tree. So you see this is kind of this complicated thing where you just boom, 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 jump around. And then the trick is, or the way that the algorithm works is, where are we going to cut this? We're going to cut this in particular places such that the similarity within the group is the highest. And it looks like this. So this is the map you're going to do in R. Okay? So it's very fancy. Right? So these are all the same color. These are all the same cluster. And basically what you set is the number of cuts, which of course defines the number of clusters. And then there's an optimization routine that looks at this. Now, yeah. The overall, the sum of the dissimilarities between all the pairs. So if they're pairwise. So it's like this was miles, right? But instead of miles, it's a distance in multivariate space. So it's an abstract number, but the further they are apart in multivariate space, the more weight. And so you want these to be as small as possible, right? So in the original geometric problem, you want to travel the shortest overall distance, right? Here you want to have the shortest overall sum of pairwise dissimilarities. And if you pay very good attention, you will make the connection to our linkage criteria. Because these pairwise distances, it's like single linkage. This is not recomputing a center for each cluster. Nothing changes. These distances, and that's why it's efficient. These distances are reused. They don't change if you say, okay, I'm going to group these together, so now the distance between these and the ones in the other cluster change, which is what we did in the hierarchical clustering procedure, right? Where we took the furthest points or the closest points or all of them, right? This basically takes the closest points and then sticks with that, because the way the minimum spanning tree is constructed by definition is it minimizes the overall sum of these discrepancies, of the pairwise discrepancies. This is the information that you get.
So you can't get this map with some other cluster?
No, no, because you can't enforce the contiguity. The reason that this works, and the only reason that this works, is this is the point of departure. This only connects pairs that are contiguous. So you will never say that, you know, well, I can't actually say this, but it's going to be highly unlikely that this one and one up north will be in the same cluster, because you force the contiguity as a constraint right off the bat. So you only group. See, because the minimum spanning tree is a subset of this overall tree, right? So it only connects units that are contiguous, right? And you cut the minimum spanning tree. So you cut subsets of units that are forced to be contiguous, right? And that's why, as I mentioned in the beginning, it's a limited search space, because you, rather than looking at all the possible combinations and then after the fact checking whether they're contiguous or not, which is another way of thinking about it, you a priori say, okay, these are the ones that are contiguous. This is a simplification of that in the most efficient way to go from A to B, B to C, and so on. And then we cut these in subgroups using the internal similarity as a criterion. So then we end up with something like this, which has a 2. You know, so given the constraint of contiguity imposed, these are the most similar internally and the most dissimilar between the two. And so this is just one example of, there's many different issues, many algorithms. There's a whole literature on this, just spatially constrained clustering. We have different search spaces. So for example, with the minimum spanning tree, that constrains our search space. Those are the only combinations we look at, the ones that are in the minimum spanning tree. The other ones, you know, we start with the full contiguity structure, but we don't look at all of them. We only look at the ones in the minimum spanning tree. And that's a downside. You know, we could be missing really good ones that are not in the initial minimum spanning tree. See, we don't recompute the minimum spanning tree. So that's one thing you could do in some of these heuristics is after you start connecting them, you could look at other ways of connecting them and see if that maybe does things better. So different conceptualizations of attribute similarity, we've been there. Different considerations of contiguity, you know, k-nearest neighbors, critical distance, we've been there, we know this. Other constraints like a minimum or a target population size in redistricting, that's the case. Or if you want to do a small area analysis and you need to reach a minimum critical value to do your proportions. The number of clusters, exogenous typically, but it could also be made endogenous. That's a problem called max P region problem, and that's a lot of fun. I happen to have worked on that, but that's besides the point. Basically, this is a very large area, and I just wanted to give you a sense that there's an other world of clustering besides local Moran, GI statistics, scan statistics, and so on. It's a big topic.